provokes mathematically and from a unprecedentedly proven physical theory that hasn't been violated to date as a constraint. That is, we observe that hydrogen is not radiating, and I invoke the constraint from Maxwell's equations. And there's a mathematics to it that has to do with looking at whatever the function is that describes the electron in Fourier space, which is k omega space. That has to deal with spatial frequency and time frequency. And the result of that, if you want to boil it down to a very simple relationship, is that if you have a function that describes the electron in space and time, and look at its Fourier transform in k omega space, it will not have components synchronous with those traveling the speed of light. That means that k cannot equal omega divided by c. And I went back and invoked that constraint, and what I discovered is that it did in fact explain why the atom is stable. It did explain why the atom has, it's observed that when you scatter electrons from the hydrogen atom, you observe neutral scattering. It explained the excited states of the hydrogen atom. It explained why those states were unstable and why they radiated. And more importantly, it predicted that you could form other stable states of hydrogen. Now, the common formula is given by the Rickenberg formula that was known in 1886. That is, the energy of the hydrogen atom is 13.6 electron volts. For n was an integer. 1, 2, 3. What I've discovered is equally valid from this Maxwellian approach is that n could equal 1 over I. So you have states that are non-radiative at 1, 1/2, 1/3, etc. Until all the electrical energy that's potential energy between the electron and proton can be released as binding energy and relativistic kinetic energy. So then, how do you make these states? If the hydrogen atom is stable at 13.6 electron volts, the theory predicted, my solution predicted, that if you had something coupled to the hydrogen atom, and there was a non-radiative energy transfer, you could get energy out of the hydrogen atom. Now, non-radiative energy transfer mechanisms are very, very common. In fact, fluorescent lights is a very good example of that. And what happens in the most common phosphor is you have antimony 3+ ions and you have manganese 2+ ions. And you have mercury vapor discharge. And the 254 angstrom or nanometer light from the mercury vapor is absorbed not by manganese, but is absorbed by antimony, and then antimony transfers that energy. Antimony transfers that energy to manganese. Technically. I don't know if I need my phone.
Just have to talk louder. It's the simplest thing. I don't know if we're going to solve it.
Okay. Is it working? Yeah, why don't you get on? So manganese accepts energy from antimony, and then manganese ion radiates. So you have a non-radiative transfer from excited antimony 3+ to manganese 2+, and manganese is responsible for the emission of phosphorescent lighting. Similarly, the hydrogen atom has, in fact, quite a lot of energy. As you know, hydrogen can undergo a reaction, an atom with another atom, to form a hydrogen molecule. Hydrogen can react with oxygen to form water. And if you ask yourself, what's the energy of the electron in the hydrogen molecule? It's 15.46, not 13.6, and there's energy that's released. It turns out that is a non-radiative mechanism also. If you look over all space, you'll see nowhere the energy for the reaction of two atoms of hydrogen forming a molecule and releasing a 4.73 eV photon. It always requires a third body to take away the energy. It's a non-radiative process. What I'm saying is non-radiative processes are very common in nature. And that's what we're using here. We're using something that can take away energy from hydrogen atoms, and it requires atomic hydrogen, that accepts it in a resonant fashion, and it turns out it's not an arbitrary number. It turns out to be the potential energy of the hydrogen atom, or a multiple thereof. So if you take atomic hydrogen, react it with something that has a net enthalpy of reaction of about 27.2 or multiple thereof, hydrogen can undergo a reaction to a lower energy state and form a new stable atomic hydrogen. That new atomic hydrogen can react and pick up an electron and form a hydride ion. So, and the hydride ions can be incorporated in any of a number of different compounds that we've synthesized, and they have quite extraordinary properties, and we're going to demonstrate some of the data from those, and we brought some of the compounds with us today. So what the theory predicts is that you can take atomic hydrogen, react it with something that will take away an energy of 27.2 electron volts and form a new tighter bound atomic hydrogen. Now, not to get into a lot of math, but it turns out that the energy as you go to these lower states goes up as an integer squared times 27.21. But the number of multipoles goes up also. Remember, you have an N, an L, and an ML quantum number? Well, here your N is your I, and you have a corresponding L from 0 to I minus 1, and you have the ML, corresponding MLs, from minus L through 0 to plus L. So you have N squared multipoles, and they're all degenerate of 27.2 electron volts, equaling the N squared times 27.2 potential energy in any one of these states. So 27.2 will take you between any successive states, because you only need to couple or react with one multipole. If you have more than one, if the integer is other than 1, for example 2, 3, 4, etc., you will go 2 steps down, 3 steps down, 4 steps down, etc. Here's a representative reaction. You use potassium ions because the first vacuum ionization energy of potassium is 4.34. The second one is 31.63. Therefore, if you take a potassium ion, a K plus, and you take and transfer electron from this K plus to that K, making it K0 and the other K2 plus, the energy of that reaction, the net enthalpy, is plus 27.28, which is the difference of 31.63 and 4.34. So two potassium ions reacting with atomic hydrogen can, in fact, cause hydrogen to go to the next successive state, which is a stable state. Potassium ions can't exist in this mixed oxidation state. They go back to K plus and K plus, releasing that initial amount of energy. And net, you have potassium going to a lower energy state and releasing energy. And that energy can undergo internal conversion because it's very, very energetic. In fact, what we'll demonstrate later in the lecture, and that'll be Dr. Ying Liu and Dr. Hans Conrads, who's graciously come all the way from Greifswald, Germany, to talk about his results, is it creates a plasma in hydrogen where otherwise there would be no plasma. I'm fine. I don't. But somebody else did.
Switches off.
Can everybody hear me okay? All right. So here's Lyman alpha, beta, gamma, and the ionization at 912 angstroms. That's 13.6 electron volts. This is a reaction where we have potassium carbonate coated on a titanium dissociator. It's run at 700 degrees centigrade, and it creates a plasma in the cell. And what you're seeing is 70,000 counts per second of extreme ultraviolet light being emitted in the cell. And we'll go into that in detail later in the lecture. There's also heat produced. This was from Penn State University. And they used the Calvé calorimeter. It converts electrical or thermal signal into electrical output. And here is a microcalorimeter, and you can see about half a watt over quite a period of time. And the significance of this is they closed it up. And if you were to burn all the hydrogen in there, and here's the particulars. 1 atmosphere in a small closed vessel running for a very long period of time. You integrate all the energy that this represents. It was 100 times more than if you burned all the hydrogen in there. And it had about 1 milligram of potassium nitrate vaporized with it. And we've done lifetime studies where we've actually gotten a couple thousand times the energy of burning nitrogen. So you can get very large amounts of energy from this reaction. And then the question is, well, what is produced? You can see extreme ultraviolet light, and you can see heat produced, and what is produced? Well, one thing about my theory that's different than quantum mechanics is you can actually solve things in closed form other than the one electron atom. And this is the closed form equation for these new hydride ions. And if you put P as 1 in here, you get 0.754 electron volts, which is the measured ionization of ordinary hydride. And if you put P as 2 in, you get the 1/2 hydride, 3, the 1/3 hydride, etc. And here's a table of the stable hydride states. And you can see here, let's say we use potassium ion. 2 potassium ions should make a 1/2 hydride at 3 electron volts. In other words, if we measure the XPS of the compound, it should have a 3 eV binding energy. And then it turns out potassium metal is perfect for a catalyst. And if you run potassium metal with atomic hydrogen, you'll have it go to P plus 3. So if you start out with ordinary atomic hydrogen, you end up in the 1/4 state. And go back to this slide. The 1/4 would have a binding energy of 11.23 electron volts. So let's look at some chemistry now and see if we in fact make that. That's fire heat. Next compound I'm going to talk about, potassium iodo hydride. It's a new compound. And the way we make it is we run a gaseous reactor, and it has in it a couple key components. You need low pressure atomic hydrogen, the torr of pressure, and this is crystalline potassium iodide, which is a white crystalline material starting material. This is a nickel or titanium screen mash, about 200 grams in a 3-liter reaction vessel. It's a stainless steel vessel. There's a source of hydrogen. Hydrogen flows into the vessel and is dissociated on the nickel or titanium that's maintained at about 700 degrees centigrade. And then we introduce a catalyst. In this particular case, we use a small amount of potassium metal that's vaporized in here, creates an atomic vapor pressure of potassium ions. And as Nelson will talk later in the lecture, you can actually see by fiber optics that there's a plasma created in the cell. It emits blue light, and you can tell what pressure and conditions are optimal to run it, and he's going to discuss that a little later. And what's formed that's about a 2.5, 3-day reaction to form the amount that's in this container. And here's the positive top sims of the compound. And you can see the K41 is really high, and that is K41. And it's because the 39 instantly saturates with this compound. It hasn't saturated with anything we've ever observed before: potassium nitrate, potassium carbonate, potassium iodide, any potassium compound we've ever looked at. 41 immediately saturates, and that's because it's in a different matrix. It behaves differently. It's very, very more ionic in terms of producing a positive ion than Ki, and it also produces a small 2+ peak, which is not seen in the control, potassium 2+. Here's the negative ion spectrum. TOF-SIMS is time of flight secondary ion mass spectroscopy. It's about 10,000 resolution. Uses a gallium beam with a large sample. And here you're looking at negative ions that are recorded in terms of time of flight to the detector. And here's the hydride ion. And you can see it's about 1 million counts. And here's the iodide, which is about the same counts. It turns out the relative sensitivity factors for all halogens are the same for TOF-SIMS. And hydride isn't really given because no one really works with hydrides for TOF-SIMS, but if it goes along the same trend, all halides, chlorides, chloride, bromide, iodide, and here hydride should be the same relative sensitivity factor. And that's also confirmed by the elemental analysis. We've had samples of this where this particular one was elemental analysis-wise, 1 part potassium, 1 part hydride, and 1 part iodide. Here's the X-ray photoelectron spectroscopy spectrum, and you can see the iodine 3 dBs, the potassium 2p3 and 1/2 right here at 292 and 295, and the iodine 4p, 4s, and here are the potassium peaks. So this is a survey, and it's potassium iodide. Hydride's the only element that doesn't have any other primary element peaks. And then if you look in the low binding energy region, I'll lay these on top of each other. Potassium iodide is on the bottom, and potassium iodo hydride is superimposed. And you can see there's something here, that's at 3 electron volts, and something here, which is 11.2 electron volts. And that's your 1/2 and your 1/4 hydride ion. Keep in mind that hydrogen doesn't have enormously huge cross-section like iodine does. So here's the NMR spectrum, ordinary potassium hydride. We'll look at NMR now. This is solid proton NMR. Spin at about 404 kilohertz, and this is recorded on a 400 megahertz machine at the National Resource Council of Canada. And here's the 2 hydride peaks, and there's some moisture in the sample, so you get this KOH, and this is a spinning sideband. And it's around close to 0 for ordinary potassium hydride. Here's the NMR of these blue crystals. You can see it's different. You have a peak here at -0.2. There's actually 3 peaks here, and there could be more than 1 species. So what we did is we exposed this to air over a period of time, and the spectrum, the NMR spectrum changes over time. You can see things are shifting to downfield, and there's still things remaining upfield. And after a long duration exposure, you can see in fact that there's something here. It's not KOH, because that was at 3.64, and then there's something 2 peaks here. There's still hydride peaks. And we've analyzed this compound by TOF-SIMS, the air reaction product, and it has fragments in it like iodine plus OH. It's got very interesting, very huge hydride, and it also has in the positive ion KHCO3 series, potassium plus potassium hydride, potassium hydrogen carbonate, which is a compound we've made, and I'll give data on that later in the lecture. We've done FTIR on this compound, and none of the peaks correspond to ordinary potassium iodide. In fact, none of the potassium iodide peaks are there. And you can tell it's an inorganic from where the peaks are, and there's no hydrocarbons present. There's no peaks for hydrocarbons. So then we wanted to examine it further. So we looked at it with liquid chromatography, with MS. And this was done in Recerca, which is a very leading lab in terms of liquid chromatography and mass spectroscopy. And they were very excited because they've never seen this ever before. This is on a C18 column. It was dissolved in 90% water, 10% methanol, and then it had a water, ammonium acetate, formic acid as it was a gradient. And that was the A component, and the B component was acetonitrile, 90%, 10% water with ammonium acetate, formic acid. And there are two peaks that gave inorganic fragments, and these correspond to, this is a 205 mass peaks, and that corresponds to potassium iodide plus potassium iodide. It's an inorganic fragment for something that's separating on a hydrocarbon column, which all inorganics come out immediately. This is a 18-chain hydrocarbon column. So it's exhibiting organic properties. And then here's the 371 peak. There's one peak there, and then there are two peaks at the 205, which means this peak gives rise to two separate peaks, or two separate fragments. It gives rise to a 205 fragment and a 371 fragment, and the other one only gives rise to a 205 fragment. There's two different components in this liquid chromatography. Again, fitting with the two types of hydrides. This particular compound we can thermally decompose. We heat up to very, very high temperatures, and this is the gas chromatograph. And this is the para and ortho-hydrogen peaks. As you know, molecular hydrogen can spins aligned or anti-parallel for the nuclei. And you can take that gas and then analyze it with mass spectroscopy. And my theory predicts, and it's a closed form equation, we'll talk about it later if we have time with the application section, that you will make a higher binding energy molecular hydrogen also. And we can talk, again, if there's enough time, we'll look at astrophysical data, because there's extremely compelling astrophysical data that this exists also. But I'll just give you the answer right now. The binding energy of the 1/2 molecule of hydrogen, corresponding to 1/2 atom, has a binding energy of 62 electron volts. It's 4 times, or n squared, that of ordinary hydrogen. And this is the time, and this is the intensity of the mass 2, 1, and 3 as a function of ionization potential. That is, we change the electron gun from 70 to 30 back to 70. And if you look at the mass 2, this one, there's very little change. Not much change. Probably just has to do with the focus of the beam. So we take the identical mass spectrometer, and we take this gas after we've thermally decomposed it, and then we do the same exact experiment at the same pressure, maximum pressure. And you can see there's about 3 orders of magnitude change, which this is just background warming. So you don't get any 2 ions until you get up to 70 electron volts. And the other thing is the fragmentation pattern is different also. Is there any questions so far? Thank you. Very good. So now we can move on to the next compound. Next thing we're going to talk about